Hi folks, so in this video what we're going to be doing is we're going to be doing the topic on axonometric projection, and we're going to be going back to the 2013 question here from the Leaving Cert. It's actually from the Leaving Cert higher level paper in the section B, question 2. And this question is actually focused here, you can see, is based on a football goals, and we're going to have to draw the axonometric views, okay, so the elevation over here, the end elevation, and then get our axonometric drawing in here, the diametric projection of it, okay. And then there might be a part C in it as well. So as always, when you've got a question, you're going to read the information that they give you. So question B2 from 2013 states, soccer is one of the most popular team sports in the world. The 3D graphic on the right shows a set of typical soccer goalposts. We can see it here. Okay. Figure B2, which is the figure down here. Okay. Figure B2 shows an incomplete diametric projection of a similar goalpost using the axonometric axes method. The elevation and end elevation or end view are shown in the required positions, and a pictorial view of the goalpost is also shown. So we can see here they've given us the end elevation, or what they call the end view. We've got the elevation here, and then we've kind of got a partially completed, you can see here they're clearly missing the curved portion of it there. We've got a partially completed axonometric projection here where we've got the diametric projection. Okay, so it says here, part A, draw the axonometric axes X, Y, and Z, and the isosceles triangle ABC. So A, B, C, and then the X, Y, Z axis. Part B, draw the elevation and end view orientated as shown and complete the axonometric projection. And then part C, we'll get onto that near the end of the question. I'll come back to that. So part A and part B. So part A, X, Y, Z axis, isosceles triangle. So looking at the drawing then, for a bit of information, we've got our y-axis here, we've got our x-axis here, and our z-axis here. This being because it's the yz, we've got our end elevation over here, and we've got our elevation over here, which is usually associated with the x and the y-axis. So, first of all, to note, the y-axis is vertical, and the x-axis is at an angle of 110 degrees from that, and likewise with the z. So that's kind of where I'm going to start with. And then you can see here, the AB line is 7 meters long. If we apply that to our scale of 1:100, that essentially means that that's going to be 17 millimeters long. Likewise up here, 8.5 meters would be 85 millimeters. 4 meters radius would be 40 millimeter radius, and then 1 meter would be a 10. Okay, so that's what we're going to do. I'm going to start off by putting in the X, Y, Z, and then we'll get on to actually drawing this structure over here. Okay, so on my sheet already, I'm after putting in the y-axis, and I've already used my protractor like this. I picked the point. If you look at my sheet there, that's the bottom of my sheet. Down here, that's kind of where I decided to start. Okay, I kept it a little bit lower down on the page, and then I measured using my protractor 110 degrees to the left, rotate my protractor this way, and I do 110 degrees to the right. So having that done, I'm now going to create my X and my Z axis. Now your axes can go off any distance, they're infinite, so they can travel any distance. So this is my X axis and this is my Z. Now both 110, which would make this angle of 140. Now if you remember back to the question, this distance here is 70 millimeters. So the best way to actually work from that is, I'm actually going to project down my y-axis, just to give me a little guide. And from that line there, I'm going to measure 35 millimeters to the left and 35 millimeters to the right. And that will be equidistant away from the X and the Z. So I'll actually just use a line here, light line, like that. And as you can see, from that point in the middle, I'm going to measure 35 to the left and 35 to the right, which will be at the 70. Now those two marks is where my line is going to be. So from there, make a little mark here. Now that I've got that mark there, I actually didn't need the other one. I've now got my line AB. So that's A, mark it there. That's B, mark it there. Okay, so there's my A and my B. Now what I want to do is, from A, I obviously want to find C. So C is going to be perpendicular to the Z axis. Now this is how I do it. I usually put the long edge of the 45 degree set square on the Z, We will be projecting out parallel to this in a while. Just to show you that, because I will be projecting this out, so I might as well bring it out now. Be using this later on. Nice and light, using red lines for my construction. But if I rotate my 45-degree set square on the long edge of the hypotenuse, like that, I have now got a perpendicular angle to that z-axis. So from A, I'm going to project up like this. Should be using the other pen there. There we go. I have now found C at the top. And now that I have C, I can bring it down and connect it to B. So there you have, I've got my axis and I've got my isosceles triangle ABC. That is part A, done. Now we have to do part B, which is, I suppose, the bonus of the question, which is drawing the elevation, end elevation, and the axonometric. So I'm going to set up my axes there. And what I'll do is I'll set up the axis for this one first. So parallel to the z-axis, like I've done here. Bit of sliding set squares here now. If you have an adjustable set square, just as helpful. So from the C, I'm going to project out. I'm going to extend this one out a little bit further. So about there. Bring this one down. There's the A. Extend it out. You can always then, once you have the directional line, extend it on a little bit further. Now that I have that, what I want to do is go perpendicular. When I say perpendicular, I'm actually going parallel to my AC line here. So to about there. I think that should be appropriate. Okay. So what you'll notice is this line, and this line are all parallel to my z-axis. And this line are obviously parallel to the AC, but they're perpendicular to the z-axis. Now what I have to do with this line here is I have to bisect that line, okay, to get the middle of it. So I'm going to get my compass there. In point right here. Take a distance that's greater than halfway. There we go. Happy with that. Get the middle of the line. Just make sure you're accurate. There's the middle of my line. Now that I got the middle, what I want to do is I want to do a semicircle. I don't actually have to draw the full semicircle, because really what we want is where the z-axis is going to cut through it. But I will put it in for demonstration purposes. Now that I've done that, where the z-axis extends on and cuts through the semicircle is a point here. I'm going to connect that to one end of the diameter of the semicircle. Extend that out, and this one up to the other end. And extend that out. Okay, so there we have that. Now, issue is, there's our axis. This point here will be a point view of the z-axis. This line is to represent the x-axis, and this line is to represent the y-axis. So technically the space in here is representing the vertical plane. Now, we know the length of it, it's 85, but unfortunately we don't have the height of it just yet. So I actually can't complete this view. I could put it in my 85, but what I'm actually going to have to do is I'm going to have to come back over to this view, because as I said, it does not give us the height. So if we zoom in here now, I'm just going to zoom in on the end elevation and think of how we're going to get this completed here. So I'm going to have to set up, like we did over here on the right hand side, my 90-degree axis that is going parallel obviously to the x-axis here, and get this in here. And then it's a case of I'm going to have to draw in this structure to work out the height. But before I even get onto this bit here, I'm going to put in the semicircle as well. So, same principles. On this side over here, I'm going to extend out the x-axis. Bit of sliding set squares. You can see here, just moving the set square around to suit myself. There's that one. Then finally, I'm going to rotate it around. It should be parallel now to the BC edge. Bring it out a nice distance. Up to about here I think would be appropriate. And then with that line, what I want to do is I want to bisect it once again to get my semicircle. to pick a distance that is greater than halfway. There we go. Now have the middle. Now that I have the middle, it's much easier for me. You can see there that's working out perfect. What I want to do now is, for the x-axis is cutting through my semicircle. I want to create my 90-degree lines that are perpendicular to one another. Once again, I always like to note, just for understanding purposes, this here now is a point view of my x-axis. Once again, this is my y, and now in this case is my z. Okay, meaning that this is actually the end vertical plane. Okay, so now what we want to do is we want to basically, if I'm just going to zoom in here, here's the object. I want to be able to draw in this structure. Now I know the distance from here to here is this distance here, 4 meters, or in this case 40 millimeters. So I can measure out along this line here 40 millimeters. When I have that done, what's important to note is I have to do then a vertical line that is obviously parallel to this line here. So if you notice, that vertical line then goes up here, but what you have to notice is where it cuts through the diameter of the semicircle at this point here, that point there then is the center point for an arc radius 40. That's going to go up to here, and then obviously we have a 1 millimeter distance, sorry, not 1 millimeter, 10 millimeters, but 1 meter distance here at the top that we're going to have to obviously cut off. It doesn't continue on, as you'll see here, like a straight curve nearly like that. It obviously gets cut, or it's a little bit flat there at the top portion. Okay, so that's what we're going to do. So, as I was saying, we're going to measure out 4 centimeters, apologies, getting my words mixed up, so 4 centimeters, and then parallel to the XY, go, slide that down there, where that goes up vertical. But what's important to note is where that line cuts through right here, at this point there, I have now found my center point. I'm now going to go across, okay, and from that point there, I'll keep my set squares here. I'm going to do a quadrant of a circle, like that. So I'm happy with that. And now, from here, I'll measure a distance of, from here out to here, 1 centimeter or 10 millimeters. And once again, just ever so lightly, use the lines that you previously drawn as a guide. So you're sliding set squares. So from that 1 centimeter out, I'll just do a line up to there like that. And from that point there, I'm going straight across. So from that point there, like this, it's going to go straight across. Like that. And there we have it. That is our end elevation, or sometimes called an end view, completed. Now that we have that completed, it's after helping me determine the overall height of my object. Just getting the curve here now. And you can see then, in relation to that, what I was referencing there, where the curve kind of continued on, straight on. Okay, so now that we have the overall height of the object, I can actually take this height from here to here. Apologies there now, guys, the lights are just going out here in the room, so I'll just have to get up and move. Apologies. There we go. So as I was saying, I'm now going to take the vertical height from here to here, and I'm going to move it over here. So that's my height. Now that I have my height there, I can put in my length, and if you remember, my length was 85 millimeters. It's going to measure 85 from the z-axis, or the z point view of the z-axis, I should say. So there's my 85. Once again, a little bit of sliding set squares here. So I'm using a red there for my construction lines. You can see here, once you have it done, you can simply rotate it then to get the perpendicular. So we have our elevation. That's that portion of it done. And while I'm at it, I'll have you in this edge here. Okay, so there is our elevation completed, and there is our end elevation completed. Now what we have to do is we have to get to this point down here before we put in, if you imagine, I'm just going to zoom in there, we will have to get a curve going here like this. But you can clearly see on the object we kind of have a flat portion here at the top, which is represented by this here before it curves. So we'll leave the curve right till the end. So in regards to that, what we're going to do is simply project back from each view parallel to the Z and X axis. So what I'm going to do first of all is, from this face over here, I'm going to project back parallel. Doesn't matter which set square you use now. In this case, I'm going to start with the X. Okay, so this X is already back. Here's an edge there. I'm going to project this one back. May not need that one. Project this one back. And then finally, I'm going to move my set square over, just so I can slide it up. Work your way around the object as needed. And then finally to this point here. Because that's the other end of the flat surface. So this one, 1, 2, 3, 4, 5. Now I'm going to bring down this point and this point. And actually, apologies, I should have noted, I'm going to take the vertical height from here, that height there as well. I should have marked that here because that's where it is on this side, and likewise here. Okay, and them 2 points I'm going to have to bring down in a minute. Now, this time parallel to the Z axis. So this one is going to project down. Come down as far as, yeah, I think that's far enough on that one. Then I'm going to project this one down. As far as I'm aware, I think it only comes to about there. And finally this one. And while I'm at it, bring down the opposite side as well. May not see all of these. We'll bring them down. And there we go. Okay. So what I want to do is I want to build this face here, the side face, before putting in the curve. So I'm going to have a straight line, a straight line, a straight line, and a straight line. So this point here comes from this height. So if you follow them down where they meet each other, it's going to be right here. The bottom one is going to meet this one right here. So if I'm accurate, they should be directly below each other. This one here is in this position in the elevation, so that's going to be here, all the way up to the topmost point. Now, if I'm accurate, should meet right there, and then this point here at the back. So we'll test our method. So that's that one. Now, if we're accurate, we'll see, depending on the accuracy here, not bad, up by about 0.5 mil. I'm happy with that though, probably 0.5 mil out there. Let's see what it's like on this one. This one's working out perfect. Then I've got this edge here. Okay, and then obviously from there it's going to curve. We'll put that in a second. Now the next portion, just going off the drawing. Now I know when it's the goals, I'm actually going to heavy in this line here because I'm going to consider that one here a goal line. Okay, we're going to consider that a goal line, so I'm going to heavy in that all the way to the edge over here, right there. And from there, it's going to go up like it does here. You can actually see it's matching up perfectly. There's the topmost point where it will be at the back. Then I'm going to get in this little bit here. And I'll heavy in here as well. Okay, and obviously it's going to curve down there, and I'm not so sure. We might see a bit of a curve, and we might have a tangential curve there at the back of it. Inside here, very similar. Actually going to heavy that there, and I'll also heavy in this portion. Now in our axonometric, we don't have to put in hidden detail inside there. Okay, let's put in that, just identify it. Okay, yeah, we probably will actually have to get the curve because we'll see it inside there. Now, that is as much of the axonometric I can draw before I move on to the curve. So what I'm going to do here for the curve is I'm going to split it up into cut sections, horizontal cutting sections. So from this line here, which we have it up to, where the curve starts, which would be at this point, I want to break it up into equal measurements. Now, the easiest here, it was a radius of 40, so the easiest thing to do here is step up in tens, 10, 20, 30, 40, okay? And then find those cut points on this surface here, and then I can find them over here to bring it down. So, from the end elevation, I'm going to mark up in multiples of 10. I should do this one here. So from the top down, you can see where my curve continued on. I'll actually do it from the bottom up, sorry. So from 4, from this point here, I'm going to do it up to 3, up to 2, 1, and I'm happy with that. Now, using a little bit of sliding set squares, I'm going to set in those cuts. There's the first one, there's the second, and there's the third. That's enough points to find. And I'm going to label those points now. I'm going to call this one 0, which is already found. This one here is 1. Then I have 2, 3, and obviously we have 4 at the top. So technically the ones we need to find are 1, 2, and 3, because I've already found 0, and I've already found, I'll put it in there, number 4. So to find those, I also have to locate them over here. So it's just going to be the vertical heights, because that's the height of my horizontal cutting section, my horizontal cutting plane. So from 0 up to 1, it's going to be here. 0 up to 2, not 0, sorry, I should say the ground up to 2. It's technically that's 0. And then finally, sorry, the ground up to 3. And obviously then we had 4 at the top. So once again, I've got 0, 1, 2, 3, and 4. So same principle is going to apply now. We're going to project those down parallel to the axis. So on this one, they're going down parallel to the z-axis. So 1 will be down in there somewhere. Likewise with 2. And likewise with 3. Okay, same principle over here. Just make sure you're accurate. So 0 is already found. If I want to find number 1, that's where number 1 is going to be. If I want to find number 2, that's where number 2 is going to be. And finally, if I want to find number 3, number 3 is going to be right here. So just to locate those, there's point number 1. Point number 2 is going to be here. And I think this one then is number 3. Yeah. So what I do then is, as best I can, freehand curve that in. And at the very end, okay, if the curve gets too steep, you could always put in another cut here and just mark it up. I'm happy with what I'm going to do here now. So this is going to come over like this. There we go. As best you can. One, two, three, and obviously 4 was at the top. Now what we have to do is, we've done the curve on one side, we now have to do the same principle and find it over here. So rather than marking all those heights up, just use a bit of sliding set squares. I find it'll be a little bit quicker. So obviously 0 is over here, it's done already. Find the 1 on this side, there. You can see how I'm lining them up over here. 2. Then finally this one over here. There we go. Okay, so with all of those, I now want to bring them down as well. It's going to go through the same lines. Might use letters for the back section, let's say. So we go A, B, C, D, and E. So technically, I found my A, it'll be there, and I found my E, it'll be there. So I have to find B, C, and D. So once again, A, B, C, D, and E. So parallel, I want to find B. So there is B. I want to find C. We may not see the C, and that's okay. It'll still give us a guide. And finally, D. In regards to D, we will see it. So there's B, C, and put in D out here. So once again, freehand the curve lightly. Sometimes it has to go up to come down. And then what you want to do is with the back curve, as best you can, you are trying to make it a tangent. That tangent actually should be parallel to the, what axis are we on? Sorry, the x-axis. So as best I can, kind of give me a guide onto my curve then as well. See, my curve there is probably a little bit too steep, so that's okay. So now I'll heavy that in. And then I'm going to see this inside portion in here. Just up to about there. Okay, so there you go, guys. That there is the axonometric projection, okay, completed, which is the part B of the question. So quite a bit in that. All right. Now what we're going to do is we're going to move on to the part C. Now on the part C, this is often the part in a question where they're trying to test your understanding of the topic. Okay, it's kind of really where I suppose you're going to get the A in the question if you're going to complete this. So it says here, a ball is positioned on the ground at a point F. Okay, so if we look down on the sheet here, you can see it. Okay, so we actually can find this point, and out here some distance, a ball is going to be here at point F. Okay, so there's the ball for a kick. Point F is 9 meters away, so we know 9 meters is going to work out when we put it into our scale. It's going to be, I'm just going to put a little arrow out here. That is going to be 90 millimeters. Okay, away from the goal line, and is located in the direction shown. And they tell us here where it is. So it's coming out from the goal line, and it's 90 millimeters or 9 meters away. The path of the ball after it is kicked is a parabola which reaches a maximum height of 6 meters, having traveled a horizontal distance of 6 meters. And essentially, a maximum height of 6 meters, having traveled a horizontal distance of 6 meters. Okay, and then by drawing the parabola in the end view, which is over here, what we're going to have to do is, by drawing the parabola or otherwise, determine whether the ball goes under or over the crossbar. So what they're saying is, when the ball is kicked, essentially, does it go under the crossbar for the goal or over, essentially, for a wide, okay? If it was a football goal, obviously it'd be a point. Now, that's essentially what we're trying to do. So sometimes in these questions, guys, they can confuse you with all the wording. Okay, so first of all, a ball is positioned on the ground at a point F. Okay, so locate the point F. Now on my drawing, point F is going to be, if you look here on the scaling triangle, okay, from here it comes straight out. So point F is going to be somewhere out along here. Okay, but it says here we don't have to worry about that. All we have to worry about is, it says here, the path of the ball after it's kicked is a parabola which reaches a maximum height. So by drawing the parabola in the end view or otherwise, determine whether the ball goes under the crossbar. So in the end view, which is this view over here, I'm going to zoom out now, we're going to have to find the location of the ball down here. Okay, so along the z-axis, or sorry, along the x edge, which is the horizontal plane, I'm going to just extend out this line. The lights are going there again, guys, so apologies. So no one's moving. Now, on that line there, and we can see here, because it's going out, if we just look here, it's going out parallel to the z-axis, so it's just straight out here. So I'm going to measure 9 meters out here. 9 meters is 90 millimeters away. Hopefully it fits on my page. It's just going off the page. So it's just out there. I'll actually just get another sheet and attach it on underneath. Sometimes when you're positioning these questions, they may not work out, especially on an A3 sheet. It'll be A2 in a leave insert exam. So just attach that on underneath there. Okay, put a little bit of masking tape. There we go. So sheet is gone, connected onto it. Okay, so with that line extended out there, just extend it on a little bit further. Move this guy out of the way. Now, over here in this section, I'm going to measure 9 meters, which is 90 millimeters. Just about there, 90 millimeters. And what I have to do is I have to sketch the path of the ball from here, which is going to be my position F. Point F there. I'll just move visualizer over a little bit so we can see it fully. There we go. So I can see where point F is, and I essentially want to find, and it tells us the information here, the path of the ball after it's kicked is a parabola. So it's going to move like this. A parabola kind of moves like this, okay, and reaches a maximum height of 6 meters. So from F, from the horizontal plane, it only goes up a height of 6 meters. So we can measure up 6. And then it says, and having traveled a distance of 6 meters. So it reaches its maximum height of 6 meters after traveling a distance of 6 meters. So from F, I'm going to mark back 6 meters, which would be 60 millimeters to here. Right there. And what I just write in there is maximum height of football. Okay, so that's the maximum height of the football at this position. So that's 6 meters high. So what we're going to do here, we're actually going to create a rectangle. This is relating back to junior cert graphics, your rectangle method, to create a parabola. So the maximum height of the parabola is at this point here. So I'm going to do a line up there. I'm going to do a line from the F as well, where the football was kicked. And then I'm going to measure 6 meters up from here. Be just to there. 60 millimeters, which would be up to there. Now from there, we'll do a horizontal line across that is going to be parallel to your XZ axis. Just make sure I've done that right. To be 100% right here. That was correct. A little bit of inaccuracy there, guys. Apologies for that. So that's where I must have slipped. So apologies there. So there we go. That there is now half of my parabola. What I'm going to do with this point up here, now called the vertex. That is 6 meters height. And you can actually see it's actually a little bit taller than our crossbar. So when the ball is kicked, it's going to go kind of like this, and it's a case of will it come back down and go inside the goals. So best way to do this, it is 60 long, 60 high. So I'm going to measure 4 equal measurements of 15. So 15, 15, and 15. Parallel to this line, I'm going to do lines parallel to my vertex line from each of those 15s. This is relating to junior cycle graphics and how you draw a parabola. And then along this side here, I'm going to measure, because it's 6 high as well, I'm going to measure down 15 4 times as well. 2, 45. There we go. Now, each one of these points on the side of our box, I'm going to connect to the vertex. That first one, the second one, the third one, and finally the fourth one. Okay. Now, what's important to note is, this is where the football was kicked. This is where the football is at its maximum height. So, where the next point of the football is as it's kicked is going to be where the first one passes through the first vertex line. So this one here. Then the next one is going to pass through the second one. You can see the pattern now, and there's the third one. So that there, if I connect all these points, will help you to make a parabolic curve using the rectangle method. So, having done it now, as best you can, you want to sketch it in. So there is half our parabola. What we want to find out in the question it says is, by drawing the parabola in the end view or otherwise, determine whether the ball goes under or over the crossbar. Okay, so what we have to do is, we've only got half the distance of the ball, we have to find the other half. Now, based on this kind of portion of the parabola, it's going to be a mirror image on the opposite side. I'm going to assume it's going to go under, but we still have to prove it. So, I've got some points here now. I can use axial symmetry on my vertex line. So from all of these guys here, if I want to find this point on the opposite side, I can bring this line across, this line across, and this one. And then using my compass, the vertex line as the axis line, take the distance to there for the first one, mark it out the opposite side, move down to the next one, distance for here. That's actually where it's going to pass through, right on the line, so it does go underneath the crossbar. And finally the third. That's all I need. Now there was a point right here, guys. So if I was to sketch that in, I'll do as best I can. So as you can see there, based on the path of the ball, I put in that is a dotted line if it was to continue on inside the goal. But at this point right here, that is the point there where the ball crosses underneath the crossbar, so it is in fact a goal. So by drawing the parabola in the end view or otherwise, determine whether the ball goes under or over the crossbar. So in this case here, just a little arrow, ball goes under crossbar. Okay, something simple like that can often be thrown at you in a higher level exam where they're trying to test your understanding. Okay, and you can see here, this in fact doesn't really relate to axonometric projection, okay, or axonometric. This actually comes from the topic of conics. So you can see here, they're introducing another topic into a question. Okay, so that's the question completed there, guys. That was the 2013 question B2 from that paper. Not too difficult question, but maybe the part C might catch some people okay there, especially when they're trying to make sense of it based on the wording of the question here and how we had to produce it. Apologies for a little error there, just a little accuracy in my set squares must have slipped. Okay, so that's the question completed there, guys. I hope you found that helpful.